So, being on SSL here, we've heard a lot of the things I was going to talk about today. But I want to try to give you some unique perspectives. I guess for my own research preferences, I've spent a lot of my career trying to find things about human behavior that are the most different from our current machine learning models. So when I was doing my PhD, everybody was trying to maximize the size of their training sets. I said, well, what happens if you just go to one example per class? And so that led to my definition of the standard paradigm of one-shot learning. So that's the kind of thing I like to do. And I'm going to try to bring in some observations about human behavior and the way I think that people learn to give us some insights, perhaps, into how SSL should be working. Deep already gave you some details about this, so I'll try to skip over those quickly. Okay, so this is all based essentially on a paper that's coming out of AI Stats this year, and it's a standard self-supervised learning paradigm with two parallel paths and a standard SSL loss as a starting point. And then what we do is we take those embeddings learned from the standard setup and we continue we project them to a new space, and we continue to, we examine the distribution of these embeddings, and we try to maximize the entropy of those embeddings. And we find that by doing so, we improve performance on downstream tasks. Okay, sorry. So after doing the continued pre-training, we pull out these features and use those on the downstream task. Okay, so that's all pretty standard. So the first question I want to dwell on is, how do you evaluate a self-supervised learning method? Now, right now, the standard approach is what I just said. We learn an embedding on a set of unlabeled images to maximize some criterion. We use those learned features to on downstream tasks, and then we just ask how well did we do on those downstream tasks. So of course, the evaluation depends on those downstream tasks. And that introduces various kinds of biases, right? Like, you're going to do well on some downstream tasks and not others. So I think there's an interesting abstract question, which is there a way that we can define an evaluation of this without a downstream task, or to think about the expectation of the performance over some distribution of downstream tasks, rather than using specific examples of downstream tasks, which is not really going to tell us exactly what we want to know. So in order to talk about this problem, to me, when we look at agents in the world, like a squirrel is born and it's going to be faced with certain difficult classification tasks, but it better start learning before it's presented with those tasks. And there's no particular reason it should know what those tasks are going to be. For example, it may need later to classify a nut as edible or not edible. But the way it's going to be presented with this task is, it sees its mother eating a nut and dying, and it sees somebody else eat a nut and not dying, and these are essentially the labels it's getting. So my point is, you don't know what the tasks are in the beginning. You're only going to know what they are later. And so how do you prepare for that? Reinforcement learning, which Jan mentioned earlier, provides another answer about the question of how an agent born into the world is supposed to learn how to act and maximize its reward. By the way, I want to give a shout out to Andy Barto, who was at UMass, who just got a Turing Award, along with Rich Sutton, for their work in RL. But this is a different point of view. I want to think about a space of possible tasks and how we prepare for those before we know what they are. So what is a random task, and how do you prepare for this virtually infinite space of tasks? Well, one interesting point is that let's say I've seen 1 million images, and then later somebody's going to come along and say, this is a subset A of those 1 million images, and here's a subset B, and now I want you to distinguish between A and B. So that would be a way of defining a task. You present a set of labels A and B, and now try to distinguish among those. Now, one thing that you might not think of immediately is that while there's an enormous number of such tasks, almost all of them are unlearnable. Okay, actually, it just occurred to me at this very moment. I was going to say something less strong, that many of them are unlearnable, but almost all of them are unlearnable, because you'll get almost all those tasks by just taking random subsets of A and B, and there's no information about how to separate those that's generalizable. Yes? Did people understand what I'm saying? So that's nice, because it means there's no point in worrying about those tasks. If we know we can't learn them, it doesn't matter how we arrange our memory. What we need to worry about is the tasks that we can learn. Now, I'm going to claim that the causality of the world suggests that there'll be, different generative causes for most of the categories that we end up being interested in, right? Like, we care about poisonous nuts and non-poisonous nuts, and those are related to generative cause in the world. And when we perceive the world and we're mapping it to an embedding, if that is a continuous map, then it sort of suggests that we have the causes with a continuous map. It suggests that the tasks that we're going to be presented with are about grouping contiguous sets of images versus other contiguous sets of images. Okay, so that dramatically reduces the set of possible tasks that we're likely to be faced with. And it also suggests things like, you probably want your embedding to be at least piecewise continuous, because if it's not, it will not correspond well to these kinds of tasks. I guess I would also suggest, so this also leads me to think about the mappings as things that maintain topology. So you have a topology of images, where if two images are within epsilon, you want to map them to 2 points in your embedding space that are within some delta. But the metric does not need to be preserved. And this relates to what Philip was talking about this morning, how these SSL methods essentially are learning metrics on these spaces. But I think in general, we would like to preserve the topology of those things. So this is just a speculation on my part, but okay. So let's try to come up with a model to talk about what it means to have a set of unknown tasks. So we can say that an agent like a squirrel is going to be presented with a sample of images from a distribution of all the images in the world, P of X, and it's just going to get a lot of these images. And then later, a task is going to be a labeling of any subset of the images with multiple labels that it's supposed to learn to distinguish between. So how can we prepare for this when we have no idea what the task is going to be? One thing to do is like what students do when they don't want to study during the semester. They just record everything and play the videos right before the final exam to try to learn everything the night before the test. And of course, the problem with this is it requires vast amounts of memory. And of course, if we have to make a decision quickly, that is, we have to learn the task quickly, then we better start learning sooner. So this is a terrible strategy, basically. Finally, if you're only learning based on the labels you receive, you're not getting the inductive bias that you can get from sort of semi-supervised learning, by looking at all the images you receive if you're only looking at the labeled images. So let's forget about this strategy. Now, here, I want to talk a little bit about the computer vision community, which is maybe a little narrower than the group of people here. But you know, people in computer vision love to try to do clustering of image categories. You know, they'll take a massive set of data and they'll do some sort of clustering to try to come up with the natural categories. And this, you know, the idea is if you have 1 million images that are unlabeled, if you could come up with all the categories, then you only need one label per class, and you've already got a perfect, you know, Bayes optimal classifier. That's pretty good. So there's a strong incentive to just learn what the natural categories are. I'll just, as an aside, I'll say there's a really strange thing that happens now in computer vision, which is that people, they're doing an SSL embedding, and they'll say, well, we want to spread out the points as much as possible to have the best embedding. And then once the points are spread out perfectly, we're going to try to cluster them. Now, I don't know about you, but if you have a bunch of points that are perfectly distributed in a unit cube or on the surface of a sphere, by definition, there are no clusters, right? It's precisely by you know, spreading them out perfectly that you've eliminated all the clusters. And people are writing papers about this on a regular basis. They say, like, you know, we learned really hard these embeddings, and now we're going to cluster these images just based on the embeddings, which is super weird. I think what they really want to do is learn an embedding and then use higher order associative information so to do the clustering, for example. And if you have a nice topological embedding, then at least the clusters will be in regions in your embedding space. So for example, if you embed images perfectly and then you start listening to the sounds made by various images, you can form clusters of dogs and cats, but you're using additional information beyond those embeddings. So I just wanted to point out this kind of odd thing that's going on a lot in computer vision these days. Not a great idea. So let's talk more about natural categories. Are there natural categories? Now, the reason I'm mentioning Aristotle is because for thousands of years, literally, people have this sense that there are unique natural categories and that there's some ground truth out there of what those natural categories are. And I think that's completely wrong. And I'll make fun of Jitendra here for a minute because he can take it. I was a postdoc at Berkeley in 2004, and everybody was talking about, okay, we've got ImageNet, this is great, it's got 1,000 image categories, but how many image categories do we actually need? And people were talking about this like, oh, there's about 30,000 natural image categories. And I was just like, that's totally, what? Like, where'd you come up with that number?
Erik, I can tell you where it's coming from. It actually comes from Irv Biederman, who actually he opened up a dictionary. There's a significant sample of how many 100 pages and counted how many nouns there was.
Okay.
And that extrapolated to the
Thank you. I should have that reference. If you could email me that would be great.
It's a number of entries in Word language.
Oh, okay. What's that?
They're text categories. They're language. Yeah, right. They're not.
No, but the computer vision people were saying there are 30,000. Yeah. Right. So you're saying the reason 30,000 came from language, not from vision. But unfortunately, that disease entered the mind of the computer vision people, and I'm not saying Jitendra does, but he started it. It's his fault. I mean, when he said it, I was literally trying not to laugh, but in 2004. So I'll give myself a little credit for that. But how do you really argue against this? I mean, so I want to argue against it by saying, what is expertise? So let's think about some people that have a lot of expertise in a particular visual area, like radiologists are experts in X-rays and CAT scans and MRI scans, and cattle farmers know a lot about how to identify cows. There's a great story about a cattle rancher that can easily identify each one of his 10,000 cattle. And whereas most of us just think there are 3 types of cattle, red, black, brown, and white. That's it. Or my cousin is a stone cutter, and he can talk about different kinds of stones for hours until you're asleep, and so on. So, you know, depending on your expertise, you can subdivide and subdivide and subdivide. And it's probably not controversial to this group, but again, I see it creeping in to computer vision all the time. So I want to stamp it out. And I'll just tell a personal story. I used to do a lot of face recognition, and I'm very sensitive to the fact that certain people actually believe that there are groups of people that look more similar than other groups of people, and it's not just that they're not as familiar with those people. So I was on this IARPA grant called Janus, and one of my teammates got up talking to 200 people saying, we all know that Chinese people look more alike than everybody else. And I was like, oh my, I was one of the most embarrassing moments of my whole career. But so I went to Senegal like 15 years ago, and when I got there, I was not very good at distinguishing among people, but then I learned that, you know, there are all these different ethnic groups like Wolof and Serer and Mende and Mendika. And in just 2 weeks being there, I learned how to distinguish among these people. I came back to Boston and I went into this convenience store that I always used to go into, and I was shocked because the guy behind the counter, who I already knew, I realized immediately that he was a Wolof. And so I greeted him on Wolof, and he practically peed in his pants. So anyway, I beat that to death, but there's a few things I want to take out of this. Not only can they be subdivided ad infinitum, but everybody has different mappings, okay? Your mappings are like proportional to the amount of experience you have. And I call this, I mean, this is a hypothesis, but I want to say the amount of representation space in an embedding that humans have, I would say, is proportional to our exposure, okay? And I call that the linearity of representation. So if you're an apple farmer and half the images you've ever seen are of apples, then half of your brain space is going to be dedicated to apples. And you're going to have a lot more ability to distinguish among them. So let's talk about the brain a little bit. So of course, there's lots of people are famous for misusing facts about brain anatomy to talk about neural networks and so forth. But how many people have seen these homunculuses? So the diagram on the upper right shows you the portion of the somatosensory cortex that's dedicated to different parts of your body. And if you look at something like the hand area, the hand is got much denser nerve endings than most of the rest of the body. And the sensory area in the brain for the hand is also much larger. So it's like proportional to the density or the space of measurements that you're taking of the hand. You also see very large areas for, say, the lips and the tongue, because they deal with eating food and sensing food, which is very important, and also, of course, language and also breathing. So these are three critical functions. There's a lot of data going to the brain, and it takes up more space in the brain. Of course, blind people have bigger auditory cortexes, violinists have bigger hand sensory areas and hand motor areas, and so forth. So the general principle is the more exposure you have to certain kinds of data, the more representation capacity you're going to have dedicated to that data. And the homunculus is just one example of that. So this figure is from a very old paper in which I was talking about linearity of probability, but the basic idea is if this were like an embedding, and you know, these might be the images I've seen of something in which I've only seen 10 of something, and you know, this is the images of something I've seen 50 of. So if every part of your embedding space gets, if each image gets one unit of area, then that immediately leads to the linearity of representation. Okay, so why would this be a good idea? Could it help us prepare for an unknown task that lies ahead? And here, again, I want to go back to this desire of computer vision people to like figure out what the categories are and arrange the data according to the categories. So if you're a computer vision person, you say, well, so imagine you're an apprentice on an apple farm, and you figure, I really need to be able to classify the different kinds of apples. So I'm gonna try to find these clusters of different kinds of apples in my observation space, and that'll prepare me for the tasks ahead. But then later you realize the tasks have nothing to do with the categories. It's more like distinguishing whether something's ripe or not, distinguishing whether something is a fungus or not, and distinguishing whether the plant is watered well enough or not. So these are totally orthogonal to the class. And it just shows you that there's no sort of breaking down of the space into a fixed set of categories that's going to solve all the problems that could come at you in the future. Okay, so this is a figure I decided I needed about 20 minutes ago, so I apologize for the low quality, but I want to argue that, you know, we're going to start talking about high entropy embeddings, and I want to talk about something that can happen if you have a low entropy embedding. So let's say you learn an embedding and it just happens to lie in a one-dimensional manifold, and these are just points for which you have no labels, but then later somebody comes along and labels these points. Now, unfortunately, if they're only along one dimension, then you have it's relatively difficult to classify them. Of course, you can learn a classifier for these, but it's relatively difficult. Whereas if you use multiple dimensions, now we can get by with a linear classifier. And this hopefully will remind you of the kernel trick with SVMs. I mean, so if you remember, when support vector machines were a big thing, if you couldn't classify something with a linear classifier, what did you do? You projected it in the higher dimension so you can still classify it with a linear classifier. So here I want to throw out another idea. I'll go back in a second, which is I want to try to draw a connection here between statistical learning theory and what we're doing with embeddings, which is, you know, statistical learning theory is about limiting the capacity of classifiers to improve generalization ability. And if you can think about embeddings as a way to prearrange data so that the simplest classifiers can have the best shot at separating the data with a small number of examples, right? So it's almost like a duel. You're rearranging the data instead of limiting the class of models that you're playing around with, okay? So what is the ideal embedding? My hypothesis is, and others have had this hypothesis, that the ideal embedding spreads out points in a feature space as much as possible. Of course, that's not quite enough, because if I have 100 images, I could literally put the first image here and the second image here and the third image here without any regards to their actual content. And then I'm going to have no generalization ability. When I project a new image, it will not go into an area that's semantically meaningful. So I need the mapping in addition to spreading things out uniformly. I need the mapping to be a smooth function, or at least a topologically consistent function with the input for the most part. And also, classic weight regularization helps ensure smoothness of mappings. So that's another way to enforce smoothness. Okay. So we're going to be maximizing the entropy of our embeddings, and many people have had this idea before. For example, in this 2018 paper, one of the first SSL methods by Wu and Stella Yu They were trying to actually minimize the likelihood function, but you can shift it around a little bit, and it's basically maximizing entropy. The problem with this was it was computationally and statistically intractable. This paper by Wang and Philip also maximized the entropy on the surface of the sphere. And what they show in this paper is that their loss function, which is basically taking every pair of points and moving them apart a little bit and then going on to another random pair of points and separating the points 2 by 2, that will eventually lead to a maximum entropy distribution, but it's going to take many, many years to get there. It's too slow, and you don't get great solutions out of it. So we're going to be proposing alternatives to these. Of course, entropy can be thought of as the spread of a distribution. I should take a moment to say it's quite different from optimizing variance, okay? Variance is about pushing things away from each other. And like if I want to maximize the variance of a distribution over 0, 1, it's a Bernoulli with 50% of the mass at 0 and 50% of the mass at 1. But if I want to maximize the entropy of a distribution over 0, 1, it's a flat distribution. So they're quite different, and many people sort of use them slightly interchangeably, but they do really different things. So that's something to keep in mind. You cannot maximize the entropy over a space like Rn because you'll just push the data to the sides forever, and there's no limit on the entropy. So we're going to consider just compact spaces, any space with like a finite integral basically, and we'll look at the unit hypercube and the surface of a hypersphere, which are two very common places you can form embeddings, okay? And of course, if we maximize the entropy, that's the same as producing a uniform distribution. Okay, so you know, in the work that we did with Deep, and I want to thank Deep for actually making this stuff work, because then I can sit up here and talk about all these abstract ideas. So we started from a BitReg embedding, which Jan mentioned earlier, and is one of the standard high-performing SSL methods. You can do a simple trick. Like we were evaluating things on compact spaces, and BitReg wasn't really compact, so we did a nonlinear transformation of the marginals to make them uniform, to make it a more fair comparison. But even after you do that, you still don't get a uniform distribution. So the idea was we want to start with an embedding like BitReg and continue to fine-tune it until we get a maxent embedding. Now, this is just 2 dimensions, and we want to do this in high dimensions, which is very challenging, or I might even say impossible. And just as a quick interlude, I'm also actually, Yi earlier mentioned channel coding, I think, and other ideas from information theory. If you're dealing with a system that has some noise in it, and you use embedding points that are not as far away as possible, then when you try to understand, so let's say I have an image and I want to map it here, but I instead map it to the pink dot that's near it. I then can't tell whether the source was the green dot or the pink dot because it's equally distant from both of them. So when you're actually trying to build memory systems using information theoretic principles, you want to use points that are as spread out as possible so that you can tolerate the most noise and still recover the original signal that's being stored. So I think there's another important way to think about what the properties of embeddings are. Is that something that we're trying to get out of embeddings or not? I'm not sure. But in general, that's a nice property of uniform embeddings, that they have this maximum robustness to noise. Okay. So what I've said so far is I want to take something like 1 million unlabeled images and map them to a uniform distribution in some typical embedding space like 512 dimensions or 2048 dimensions. This all sounds like it should be very straightforward. So what's the problem? Well, first of all, the sample complexity of this is really horrible, and I'm going to talk about that more in a second. And second, we're not actually dealing with distributions. We're dealing with finite points, and no matter where you put those points, when you measure the entropy, you get minus infinity. So what you're really trying to do is you're trying to pretend like the points were a draw from a distribution and move the points so that it looks like they came from a maxent distribution, which is not exactly maximizing their entropy. In fact, it's more like sphere packing, which I also heard somebody who mentioned sphere packing. It might have been Yi too. Yeah, it's more like sphere packing. Okay, so let me go into a little more detail about these. So, I've done a lot of work in entropy estimation, and I run into a lot of people. I tell them you can't estimate the entropy of a distribution with more than like 5 or 6 dimensions without enormous amounts of data, and they don't really believe it. They don't feel it. They want to say it's not true. And so the purpose of this slide is to try to make you feel this, so you really believe it. Okay. So Alice and Bob are standing in the Sahara Desert, and I'm going to tell them, I want you guys to maximize your entropy as though you were points from a distribution. And so they decide, well, we should probably get further apart, which ironically is more like maximizing variance, but it's not a bad strategy for entropy either at first. So they walk away from each other for a few hours, and then they get really tired and hot and say, are we done yet? And so they start like this and they end up like this. Is the distribution from which these came higher or lower entropy from the distribution from which these came? You have no idea. I mean, it's a completely, you're not even close to the number of samples you need to get that kind of estimate. Now, why am I talking about this? Since we have 1 million points or maybe 10 million points. Well, the problem is, even though we have 10 million points or 1 million points, say 1 million unlabeled images that we're putting into our embedding space, we have 2048 dimensions. So I want you to think about the idea that we have enough points to put an image at every vertex of our embedding cube. Now, how many such points do we need? Well, if we're in 2048 dimensions, there are 2 to the 2048 vertices. That is a ridiculously huge number. Well, we have a lot of points, right? We have 1 million points. That's only 2 to the 20th instead of 2 to the 2000. Okay, so not only is it hard to estimate, it's a ridiculous problem. You can't even do anything sensible. Are you skeptical? No, you look skeptical. Let's talk. That you're the kind of person I'm trying to convert. They're like magic, right? Okay.
Is it might there be some kind of an implicit bias when you train them so that maximize the variance you avoid this problem?
Well, it's interesting you say that because I will talk about the inductive bias of these in a little bit, okay? But you can't really solve this problem. Okay, so you don't have enough data. Let's see. Now, is your name Bob? No. Let's just pretend it's Bob. So Bob says, that's not true. You can estimate the entropy of a high dimensional distribution if it lies in a low dimensional manifold. And there were a lot of people talking about low dimensional manifolds. But the whole point here is that we don't want our embeddings to be in a low dimensional manifold. We want them to use the space, to spread out the representation so that we have as many ways as possible of doing discrimination in that space. So that's exactly what we don't want to do. So it's not helpful. Okay. All right. So now I'm going to tell you a little bit more about what our solution was. Deep gave a very nice and quick summary, so let me go into a little more detail. So there's two different characterizations of a uniform distribution over a unit cube in three. I'm going to use 3 dimensions in my example. So imagine the dimensions are x, y, and z. A uniform distribution maximizes the joint entropy. So it's the max over h of x, y, z, where h is the differential entropy. And a second characterization that's equivalent mathematically is that you meet both of these conditions. All the marginals are maximum entropy. So I maximize h of x independently with h of y and h of z. Those all have to be uniform. And I also need an additional requirement, which is that the marginal or that the features are jointly independent or statistically jointly independent, which simply is satisfying this criterion here. So while we can't really estimate joint entropy directly, do we have enough data to measure the entropy of the one-dimensional marginals? And the answer is yes, easily. We have 1 million points for each marginal. We have very, very accurate entropy estimators for that kind of data. But do we have enough data to measure joint independence? And the answer is no. Estimating joint independence is basically just as bad as estimating entropy. But what we can do is we can make a compromise here and use linear independence instead of full statistical independence. And that's exactly what methods like VicReg and was it Barlow twins and a couple of other methods have used to decorrelate the data. So we're doing full joint decorrelation, which is tractable. So there could be, so if we achieve linear independence and max marginal things, we could still have some structure in our joint distribution. For example, we could have parity. We could, the parity of x and y and z could be structured. And we won't discover that, and it'll be structure hidden in our data that we can't get rid of, which would mean it is not maximum entropy. So really, the next most interesting question to me is, if you maximize the marginal entropies and you ensure linear independence through decorrelation, is there any structure left in your data? Or do you somehow magically get rid of it, maybe because of the inductive bias of the neural network? Maybe. Guess what? The answer is. So just to summarize, we're going to do an embedding based on maximizing individual marginal entropies, which is just the entropy of each feature of your embedding. Maximize the linear independence by minimizing the off-diagonal covariance terms, and then we'll also apply an L2 penalty on the weights to make sure that our embedding function is not too crazy. It's like smooth. Okay. So now Deep already went over this, but I'll say it again quickly. We're trying to create a uniform distribution, and we're doing that by creating. If you look at the far right there, we've got nice uniform marginals, and we also have independent components. Z1 and Z2 are not only linearly independent, they're also fully statistically independent. So that's what we're hoping for. Now, this distribution, the marginals are perfectly max-ent, they're uniform marginals, but they're also perfectly correlated. So you can get this solution if you don't include a decorrelation term. Now, as Deep already mentioned, there are distributions like this X distribution that have max-ent marginals, and they also are decorrelated. So both of these two right distributions optimize our optimization criterion. And so the question is, are we going to get the thing in the upper right or in the lower right? Okay. And So I'll just hop down to here and practice. We seem to get results more like the first case, like the case on the upper right. And that's good, but why do we get that? So our hypothesis is that the natural inductive bias of the neural nets makes it difficult to produce distributions like the X distribution. If you think about what kind of a map takes, you have a nice smooth map that can produce a uniform distribution. If you want to produce an X distribution, our hypothesis is that that's more difficult given the continuity and the inductive bias of neural nets. Okay, so we seem to be getting these things like the upper right, even though they're not technically part of our loss function. So any questions about that? Yeah.
Does it depend on the dimensionality of the input?
Well, we're using like image data, so it's high dimensional. Is that what you?
Well, from my experience, you can easily get the X in a low dimensional information. So from my experience, you can easily get the X if the input dimensionality is small. So let's say
Yeah.
2.
Oh, I see what you're saying.
But the larger the dimension, you suddenly get that, the
Yeah.
upper right.
Yeah, that's an interesting case. I don't think we've played around with low dimensional data. Yeah, good, interesting. Yeah, that could make sense. So I just want to make one other point about this. Well, so are we successful at getting high entropy distributions in these large embedding spaces? And the answer is we can't get the answer because, as I said, we can't estimate the entropy of those distributions. But what we can do is we can look at our one-dimensional marginals and see that they're very, very good. Okay, well, that was part of our loss function, so that shouldn't be too surprising. But what's more interesting is when we look at our two-dimensional marginals. So we take our, if we're in 2,000 dimensions, we can pick any pair of dimensions and project everything down to those two-dimensional marginals. And those distributions are very, very high entropy, even though we were not ever optimizing those directly, because we were only optimizing one-dimensional marginals and decorrelating. So that suggests, at least for pairs of dimensions, we're not getting any X distributions. Now, of course, you'd have to check that for three-dimensional marginals and four-dimensional marginals up to 2,047 dimensional marginals, and we can't really do any of that, but it is encouraging. Okay, blah, 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 blah. Oh, yeah, and so this is a nice slide that Deep didn't have time to describe. What this shows is a distribution of nearest neighbor distances compared to 100th nearest neighbor distances. So before and after, we've tried to push our data points apart. And basically what this slide shows is that many of the 100th nearest neighbor distances are actually closer for some points than the nearest neighbors of other points, which is a sign that you're highly non-uniform. After our processing, we get much better results in those regards. So most points have very nearby nearest neighbors and far away 100th nearest neighbors. It's still not perfect, as you can see, but it's much, much better. Okay, so that's another way to examine the results. Okay, I've been there. Oh, and this is just another look at what our model actually does. So I want these two flat curves here are the standard SWAV SSL model and the VicReg model. Yeah, and so yeah, this is VicReg here, and this is SWAV. And at 10 epochs of training, we look at their top one accuracy on downstream task. And but if we continue pre-training with our max end objective, then we do better. of course, we continue the training for the standard models as well, just to make it fair. Okay.
This is full fine tuning or linear probing?
Oh, sorry. Did everybody hear that? Okay, thanks. Okay, so, I'm out of time. So I'll just say, if you want to take, if you didn't learn anything else from this, I recommend you look up the M spacing's entropy estimate. It's much better than almost everything that's used in the machine learning literature. It's from 1973 by Aldrich Vazicek. So check it out. It's highly efficient in the statistical sense. It's accurate and it's differentiable. It's super simple to implement. And another tip is, this is a cool thing, and then I'll stop, which is I've talked about maximizing entropy in a unit cube. It turns out it's really easy to maximize entropy on the surface of a unit sphere by using the following trick. How many people know how to sample from the surface of a unit sphere? What do you do? How do you do it? Yes, exactly. So in 3D, you pick 3 Gaussian points and normalize it. Well, if you think about it, this tells you how to put uniform points on a sphere. You pick, you basically force the marginals to be Gaussians, and then you project them. So what you have to do to maxent on a sphere is to push all your marginals to unit variance zero mean Gaussians, and then when you're done, just normalize them, and you got it. So you get a super uniform distribution. Yeah. So I mean, I assume this trick was known, but I haven't been able to find it anywhere else. But obviously, you knew about it. So okay, I think I'm done. And thank you for your attention.